Now there is one announcement. Now you are waiting for the lunch. Lunch is arranged just at the left side of the corridor at the end near computer engineering department. There is open space, so lunch is arranged. All are requested to join for the lunch, and our next session will start sharp at 2 o'clock. So all are requested to join on time. Thank you.
Announcement is Mr. Jain Kulkarni has announced a donation to ISSE 1.25 lakhs. So big applause for Mr. Jain Kulkarni. And all our well-wishers, I appeal those who wish to go for ISSE, you are welcome in any form. You can share your experience for our technical journal. You can participate in our activities. You can of course donate generously to ISSE. So that is my appeal to you. Thank you very much.
So after a delicious lunch, we now start with the technical session number 2. This session starts with the presentation on pre-draft IS 13935, and it will be explained by Engineer Jaswant Arlekar sir. Brief introduction of Arlekar sir. Jaswant N. Arlekar is a practicing civil engineer and structural engineer and an adjunct professor at the National Center of Disaster Mitigation and Management, Malviya National Institute of Technology, Jaipur. He holds a PhD from IIT Kanpur with a professional experience, practice, research and teaching of over 20 years. He has conducted short courses on subject of analysis, design and detailing of structural steel. He has designed and executed several residential, commercial, public, auditoriums and industrial projects in reinforced concrete and structural steel. He also has experience in assessment, repair and retrofit of structures with a special emphasis on earthquake-related safety. He is a member of Code Committee of Bureau of Indian Standards and Indian Road Congress. So now I request Arlekar sir to take charge of the mic and start the presentation.
Thank you. Welcome back. I hope you've had a good lunch because I've been given 1 hour to do this. Actually, I need 2. So we'll try to finish it in 1. Let's see how much time I take. So, in terms of doing this, as said, Professor MURTY was supposed to come for this, but unfortunately there's some emergency. I know you're expecting Professor MURTY to do this, but please listen to me. Maybe I won't be Professor MURTY, but I'll try to do some justice to this. Okay, the main agenda of doing this was, like in the morning Professor GOSWAMI explained, we have 3 verticals in our code. 1893, which addresses the hazard, the loading and the analysis part. 13920, the detailing and design part. And then there is this 13935. This is a new number that has come. But this is basically going to address all our existing buildings, the existing stock of housing which is there in India. How to take care of them, because it's, as structural engineers here, you would appreciate that demolishing a building after 50 years is not a possibility that we look forward to. Anybody will not allow you to do that. We have, in this city itself, buildings which are much more than 50 years. So we need to have some methodology, we need to have some way of making sure that this building can be extended, the life can be extended. Before that, we need to assess and see what is the way to find out what is the potential of the building to extend the life. If not, how to retrofit them. So this is the code that is going to look at this aspect where we assess the building, repair the building, retrofit the building, and do the overall evaluation, say that okay, this building is okay to extend the life. go with a few pictures that I have collected over a few years. 10 years fire brigade got 3,000 plus calls in about 10 years for building collapse, not because of earthquake. This is only in Mumbai. In the last 10 years, we have not had any earthquake which would collapse the building. So we have a problem of buildings not, they just collapse. We know, I mean, all of you are aware of some buildings which are just going down. So as per the requirement, there are about 15,000 buildings in the island city. And with the current speed and with the current know-how of redeveloping and the current capacity that we have, it will take about 200 years. This is an article in Times of India in 2021. So it's not a solution. Redeveloping a building or the buildings, the stock of buildings that we have is not a solution. So we need to figure out a way of. So we do have a way of doing it. We do structural audits of building. How we do it? What is the rigor that is involved? That is the next level that we go. We do have a system of taking care of such buildings. And structural audits and repairs should be an interim measure to ensure life safety of such buildings. Another pictorial which shows what was the problem with this building. I don't want to talk about this. Earlier it was fine. Yeah. Hopefully this is better. So the message that we are taking from this, most of our buildings which are 15,000 stock that we are talking about are not in very good conditions. They are, from medium, moderate to poor condition type of a situation. So the solution that we are talking about is how to assess them, how to retrofit them. Another pictorial similar, 2021 August, there was a mass evacuation of 4 or 5 buildings in Ulhasnagar which were about to collapse. People were taken out. No lives were lost in this. But earlier, before this, there were some people who lost their lives. This another picture. Nobody died in this. Unfortunately, this Mr. Sundar Shaw was standing on the pavement. The building collapsed. He was not a resident of the building. So, unfortunate, very unlucky. So, interim solution, we look at how to ensure life safety of the residents and overall safety of the building through structural audit and repairs. We need to understand how to assess the building and repair it. Some more pictures which I have collected. I will run through this very quickly. Oh. Excuse me. Be able to use. So, just basics of structural engineering. and earthquake design. So we look at design loads which are force loads, then there are displacement loads. This we understand very well. The people who are here will understand this very well. Force loads are dead loads, imposed loads, wind loads, snow loads. All the loads which actually apply a force on a building. This light is actually disturbing. ये light थोड़ा dim करना है. Impact load, construction load, stressing. These are all force-based load. In parallel to that are displacement load, particularly the earthquake load that we are worried about or we are concerned with. In addition to that, there are temperature creep, shrinkage, elastic shortening, foundation settlement. And earthquake load is one that we are looking at, and this code is going to be focused on assessment of earthquake loads and their effects on the building. So quickly, what is an earthquake? It's a ground motion, it's energy release, waves travel, they come up to the surface, they affect our structure because the ground is moving. So movement of the ground translate into movement of the building because of inertial effects, and that is how deformation happens in the building, and that is how the force is generated, that is how the building gets damaged. So when there is an earthquake, ground moves, there's deformation because of the inertial action caused by the acceleration in the ground. So when you look at force displacement, in minor earthquake, there's some force that comes in the building. In a moderate earthquake, slightly higher force. In severe earthquake, larger displacement because the structure is going into some kind of inelastic behavior or some damage in the structure. And that's how the load displacement curve is drawn, or this is the behavior of the structure. So there are three levels of earthquakes that we need to consider usually: minor, moderate, and severe. In severe, we will expect a lot of damage in the structure. In moderate earthquake, little damage. In small earthquakes, we should not expect any damage. We should be able to use the structure very quickly and come back and continue with our business. Earthquake versus wind, like I explained. Wind is a force-based loading on the structure. It's a force physically applied by the movement of the wind because the structure is blocking it. The force gets created on the structure. But earthquake is not like that. Earthquake is a movement of the ground. Because of inertia, there's deformation in the structure, and that is how the forces are created. Because one column, 2 points of the column are going in the opposite direction. That is how forces are generated in those structural members. So if you look at wind-based loading, this is an everyday load, almost everyday load. Earthquake will happen once, maybe twice, or maybe never in the life of the structure. So there is a probabilistic assessment in the earthquake saying that, like in the morning we were discussing return periods of earthquake. That is how we assess the earthquake. We don't design the earthquake for the full load, we design for a lower load because we expect damage in the structure. Because of the damage, it's a reduced load that is coming in the structure. So wind load is a force space, that's the green part of the thing, where we have the stiffness of the structure. And because of the stiffness, that is force is applied on it, those are the forces which are generated, the reactions of the force that is applied, generated in the structural members, and we design for that. Straightforward, very easy to understand. But earthquake is deformation applied. Because of the deformation, there is some change in the structure, and corresponding to that, we say this is the equivalent force that can be generated in the structure, and we design it for that structure. So it's basically deformation, structure moves, and we say this is the equivalent force in the structure. So that's how the design is categorized, force-based design and deformation design. So when we talk about, we've seen this in the morning, 7 virtues that we look at. One is the configuration, we make the structure good. All the good things of the structure, good column, good spacing of the column, good grid, good material, good construction practices, no irregularities. That's the configuration of the structure. Start with a good structure. Then you provide minimum stiffness in the structure. Minimum stiffness required, which is code based. Then you have minimum level of strength, that is like whatever the code says, the PP is the minimum force that you have to design for. That's not the force you have to design, you can design for a higher also. Then there's ductility, because of the damage that is coming in the structure. While the structure is getting damaged with the earthquake force, the structure should not collapse. So primary goal that we are trying to achieve is the structure can sustain damage in an earthquake, but it should not collapse. So collapse of the structure is basically a prohibited thing. So don't let the structure collapse. Let there be maximum damage in the structure. you walk out. In the morning, director VJTI said he experienced some earthquake in Guwahati. They were shaking in the middle of the night. They walked out the structure and they went on the road and stood. That is the kind of status that we have to achieve. Shaking in the structure, even major damage, but no life fatalities. So life safety is the prime objective that we are looking at. Then along with ductility, deformability, because the movement is there, the structure should be able to deform to a certain extent without collapsing. And this can be complemented with a desired collapse mechanism. You say that only specific parts of the structure will sustain damage. Like in the beam, at the ends of the beam near the column, there will be some kind of damage that will happen. That will help us in dissipating the energy that is fed by the earthquake. Or you have other places and not in the column. Like if you have a plastic hinge in the column or hinge in the column, the structure will collapse very quickly. So place the hinges in the beams. That is how the code also addresses. This code tells us to do a strong column, weak beam design in case of buildings, where the columns are very strong, the plastic hinge or damage happens only in the beam, the collapse probability is much lesser and it can sustain much more deformation, much more energy dissipation can be applied. And the seventh virtue is the energy that we are able to dissipate when the structure has been subjected to an earthquake. So, repeating, 3, strength, configuration, stiffness and strength, minimum, good configuration, minimum stiffness, minimum strength, then ductility and deformation, because we are expecting damage in an earthquake, it should be able to deform, and the ductility of the members will be giving that deformation capacity to the building. For assessing this, we'll need some type of nonlinear analysis. Right now, the first 3, 1, 2, 3 are we are able to achieve 1, 2, 3 based on the elastic design, elastic analysis. But 2 and 3 to assess and say that yes, this structure has these 2 features, we'll need some kind of nonlinear analysis. Collapse mechanism, like we said, strong column, weak beam, is a provision that is given in the code. It's a prescriptive provision. But to say that yes, this structure is able to achieve that goal of strong column, weak beam, is the collapse mechanism that we assess the structure, do some kind of analysis. And then the next stage would be, as a follow stage, would be to see what is the energy dissipation capacity of the structure. So this 7 virtues. So when we have earthquakes, we have column structure and we have wall structure. We know, and through experience, through analysis, through a lot of design that people have done, walls are able to sustain larger deformation. Columns will be able to take higher load, but walls will be able to take higher load as well as a lot of deformation capacity which will be available. Like, that's why we are trying to push, or the earthquake codes that are coming in the country now are trying to push towards wall construction rather than just moment resisting frame with columns and beams. Particularly to achieve the deformation capacity which will be based on the ductility that we achieved in the structure. So, the minimum is lateral stiffness, overall strength and deformability. These are the 3 things that we need to do, and we are currently actually trying to do that, and if we design as per the code, we think that we'll be able to achieve all these 3 aspects that are required by the code. So, with this background of earthquake behavior and analysis and the design, we see what is required for earthquake safety assessment. To retrofit a structure, we need to first understand what the structure is capable of, do the assessment, some analysis, some preliminary design, some, what is the configuration of structure. All those put together, we come up with a plan of whether the structure is okay or not okay. If not okay, what is the next step to be done? Some nomenclature, I'll just explain. Retrofit, remodel and repair. These are the 3 things. I'm sure none of us are confused with this, I just want to put it out there. Retrofit is basically where you strengthen the structure. Retro is like previous and then you fit it. Remodeling is changing in the configuration, and repair is repair. If something is wrong, if there's a crack, you open it up, repair it. So in retrofit, you basically increase the structural capacity. You look at the structural capacity and check its adequacy, and if not adequate, then you improve it. Remodeling is functional change in the structure. You check out some walls, check out some beams, add some walls. So that kind of a repair. and they may not be structural, but remodeling will also include non-structural changes to the building. Repair is just visual improvement, painting, repair of plasters, or some spalling of concrete has happened, you know, put the reinforcement back, do some kind of drilling, and repair the structure. So basically, visual improvement is basically correlated to repair. Most of the buildings that we see which are being repaired, this is the third part that is getting done, where we just restore the structure back to its original condition, the existing condition, and there is no increase in structural capacity. So in the retrofit, there are three again: restoration retrofit, where you bring back the structure to its original capacity. Then there's an upgrade, you increase its capacity. It can take a larger earthquake, can take higher forces, can take higher load. And then there's a rearrangement in structural capacity, where you say that, okay, this structure is not capable in the current configuration, I'm not able to upgrade it, nor I'm able to restore it, but I need to make some structural configuration. You add some members, you add braces, or you add structural walls, or you add buttresses in the structure. That is the rearrangement that will happen. And in rearrangement, sometimes we downgrade the structure also. Like there are many bridges which exist across internationally, where they downgrade the class of load that the bridge is capable of taking on. So that is another method of increasing the life of the sustainability model, where you say you don't load the structure to that level, lower the loading, now the structure is okay to take that load. But remember, retrofit and repair are not synonymous. Repair is repair, it's visual, and retrofit is adding strength to the structure by these three methods, where restore, upgrade, or rearrange. So we are improving the structure. One is increasing its capacity, and in rearranging or in reducing the capacity, we reduce the capacity. So if the capacity cannot come up to that level, we reduce the demand on the structure and bring them at par. So quickly go through what current practice is in Mumbai, across the country also. Condition assessment is done. We do visual assessment. We look at all the cracks, repairs, leakages, spalling of concrete, exposure of reinforcement. Do some structural identification. Many times the drawings are not available. We have some drawings available. We identify which is the column, which is the beam, what is the size of the beam, what is the size of the column. We do some kind of non-destructive testing, destructive testing, and identify what is the material. Again, we do some assumptions and say, okay, this is the structure right now, and what do I do for the repair of the structure? We go back and the most of the effort here is to restore the structure to its current condition. Whatever the condition it was maybe 6 months ago, 1 year, 2 years ago, we restore it by taking out bad concrete, we replace it with some polymer concrete or mortar, or maybe micro concrete type of thing. Or if the reinforcement is corroded, we replace that reinforcement with the best method that we have. We replace this reinforcement and say that this size is same, reinforcement has come back to its original number, and now the structure is okay, it is okay as per the existing condition, existing design it was there. That was the current existing practice. In the desired practice, what all of us want, I mean, I can say this for all the structural engineers here, that this is the minimum required. Most of us are doing this. The next level is to actually go back to the structure after getting all the information, making assumptions, all the information that you have. Let us say we have 80% of the information. We go back and perform a structural analysis. We check the configuration, update the loading, check the structural design of the existing structure. With all your experience, all your assumptions, all the knowledge that you have collected about the structure, whether it is through drawings or I'm sorry, okay. The chart is gone. So we were talking about the current practice. And then we are looking at what the desired practice should be. We look at the structure, we do all the assumptions, we get all the information, we make our judgment calls about loading, configuration of the structure, the structural member sizes, reinforcement, everything. We make an assumption. Let's say we are at a stage where we understand the structure, sort of understand the structure. Then it comes back to your original design, I mean new building design. You have the structure, now you have to design and check whether the structure is okay for all the code requirements and the structural behavior. So structural analysis using configuration of the structure and updated loading, because we want to qualify the structure for the current loading system, whatever the current codes are saying. Then check the structural design for performance, evaluate the performance of the structure as per the standard and say whether the structure is okay or not, and then go into construction and do the structural upgrade. So that is what we desire, that is what we want now. The top part that we are doing, and this obviously comes with certification like it does for the new buildings. At the end of the building of the new structure, we have to certify that the design is adequate as per the code, and we take responsibility for the design. Similar thing is expected here also, where we do the structural analysis, structural design, structural construction, and say that this is okay for occupation now. So that is what the desired practice should be. So when you look at new structures, you estimate the load, analyze the structure, design in detail, and then construct. It's top-down process, simple process. We make all the assumption and we implement it and achieve the structure that we want to have. But it's not the process standards that are familiar to this process these are the standards that we use. Construction, there are many standards of construction, quality of construction, management of construction. So those are the standards which are used by the construction industry. But if you look at the existing structures, we have to assess it first. We have to understand what is the existing condition of the structure, what is the existing configuration of the structure, what is the capability of the structure. That comes as assessment, and then combined with analysis, we go back and evaluate for adequacy. We do assessment, analysis, and design, and then we evaluate, say that this is adequate as per the relevant standards. And that is the reverse process, where you already are given a structure and you say whether it's okay or not, and then do some kind of intervention. So again, just revising this: configuration, stiffness, minimum strength, ductility, which comes along with deformability, desired collapse mechanism, and energy cell. This was shown earlier in the morning also. I want to go through this again and again, because this, if you understand this, it will be easier to conceptualize and imagine a structure having all this feature, or whether the structure has a few of this feature, and how to bring this feature to the structure would be easier for the structural engineer. So when we look at retrofit, that's the original design. Damaged state of the structure would be reduced, both the strength as well as the deformation capability of the structure will be damaged. And if we are able to achieve the retrofit of the, that is the curve that will come, where we restore the structure to its original configuration based on what it was designed for. But there's one small change in this that I would like to state. We have to see how to come to that. The original structure was designed about 50-60 years ago. At that point in whatever the standards were, now the standards have changed substantially. Whether we bring the standards into the picture or not is the question that we need to collectively answer. Then we have retrofit in terms of upgrade, where we have original damage, and the retrofit in terms of upgrade, the nomenclature that we talked about. The top curve, where there is an increase in the structural strength as well as the structural deformation capacity. Then there is this remodeling, original structure, damaged structure. Remodel will be somewhere in between. We make some changes, and based on our understanding of behavior of the structure and the loading, we say that slight increase we may be able to achieve. We look at repair. In repair, we are actually going back to its original configuration. You achieve at the damage stage, if you just take out plaster, if you just take out cover concrete and replace it with mortar or micro concrete, you're not going to add any value to it. You're going to restore its damaged state. Just visually you will be able to say this is looking good, the beam is good, but you have not done the due diligence of assessing and checking the structure whether it is capable of taking the expected loads or not. So if you look at all those three together, a retrofit, upgrade, retrofit, restore, remodel and repair. This is the levels that we will achieve in terms of how the structure is going to serve us for the remaining life for its remaining life. So when we look at another pictorial, we're trying to basically put in different ways of understanding what this process of assessing and retrofit entails. This is the normal life of the structure, and if there are all these deteriorating characteristics which are imposed on the structure, where there is sulfate, HI, carbonation, concrete, then some damage, bad use, leakage, corrosion, all those, then you have the behavior of the structure would be like this. The damage would occur very quickly in a shorter time, and damage will mount on to, the increase in damage would be the third curve that I've shown there in red. So normal life of the structure without all these problems is what we are expecting, but with these in picture, we'll have a problem of how to then make the structure livable, then make the structure safe to live in. So that gives the reduced life of the structure from the normal to back based on whatever kind of environmental factors are affecting the structure. So if you look at the behavior of the structure, if you have a capacity of the structure which is degrading over time, life as in time, and the capacity of the structure, if you at some point in time say that I want to do a restoration, retrofit or upgrade or one of those, then if you do it earlier, you may be able to extend the life of the structure by a little bit. If you do a late retrofit, because the structure has gone down so much, getting in all those features of the structure compounded with the new standards, we may not be able to achieve the extension in the life of the structure. It's not that we will not be able to achieve, but the difficulty level will be higher. The effort that we need to put in, the money that we have to spend would be much larger when we do a late retrofit. So combining this together, there are two pictures that are drawn here. Performance of the building at different levels, target limit, service limit and safety limit. So if you do an intervention, a repair or retrofit at some point in time, you increase the life of the structure, and the structure now is brought back to its good state where it can take sustained loads. But at a certain time of the structure where it's highly degraded, going in for retrofit is going to be more and more difficult. The second picture on the right hand side, we are trying to show if you do periodic maintenance, which will cost less. It's not a big chunk of money that is required at one point in time. You do periodic maintenance, you may be able to extend the life of the structure for a very large, for a longer period, but keeping the level or the health of the structure at a higher level, rather than coming down and doing a one-time retrofit, which may not be so easily possible. So another pictorial where we say how the structure behaves. If you go in for repair, you are actually just restoring the structure at its current level. There is no added value in terms of behavior of the structure or the capacity of the structure. So there's no improvement. In case of the design load, the structure will not be able to perform the way it is supposed to perform. So again, saying that structural repair is not structural retrofit. So we have to come out of this, that if you just do some kind of restoration repair, it amounts to a retrofit of the structure. So we right now don't have a compiled document, or we don't have compiled guidance which tells us how to do this. The effort of BIS CED 39 is to create a document which will be able to guide us in taking this forward. So when we are looking at restoration, we are looking at upgrade, we are looking at remodeling, or when we are looking at retrofit. Why are we doing this? Because there is some deficiency that is there originally in the structure, or something has happened to the structure where the structural capacity is degraded. Either it is the environmental conditions that we looked at, or the change in codal provisions, or one where we say insufficient load combinations considered. So you would have under-designed the beam, or you have bad connection. The connections are not designed. Strong column, weak beam has not been followed. Because of the way the structure behaves during an earthquake shaking. And then there's large deformation because of this L shape at the ends. And we need to see how to avoid this and how to take care of. If not, then how to take care of this. And we do have structure like this right here in this city, which is like a plus-shaped structure. This is one structure in Goregaon, where it's not on a hill, but it has a plus shape, so in this point basically the stress concentration would come in. Then we have the effects of the entrant corner. This is very well captured in this literature. Some concepts of earthquake resistant behavior of building. This book is written by CVR Murthy and RUPEN GOSWAMI. They have covered various configurations that we should look out for, and they have shown pictorial representation of what happens if this is the type of structure. Like if you see in this, because of this type of deformation, there's a stress concentration at the joints or the re-entrant corners. Then we have irregular geometries. This is again covered in the code. What is to be done with this is also given the current draft of the code. Earlier code was also talking about it very subtly, it was talking about, but now the revised code that is coming out is explicitly talking about how to take care of this and how to avoid this, and at what level you have to say that this is not allowed, this is prohibited. So these are the problem points in these types of buildings. At the re-entrant, wherever there is a change in geometry is the problem basically. So it's a very layman type of terms if you use. Wherever there's a change in geometry, change in shape, would have a problem with the re-entrant corner. This is a famous building in Bombay. This is the typewriter building, which basically is the stepped building that the code talks about. So this is another building, which is basically the inverted building. So there are 3 plus 3, 9 columns at the base, and then there are cantilevers which are coming out by about 7 meters. So this is a typical case that has been covered in our code actually. So we have this irregularities. What happens when we have such a configuration? It's explained in this book. What would be the condition of the structure if a design level earthquake strikes? So if you get if you have the time, this book is freely available on the internet. You should go through this, and it gives a lot of insight into what behavior is and how to avoid such behaviors. Then we have open ground story, which is a traditional problem building for us across the country. We have seen this in many of the earthquakes has seen this, whether it's Bhuj or Chamoli or even Jabalpur earthquake, and even before that in the Kilario. Some cases of open ground story, weak story was noticed, and we have been struggling with this problem, how to avoid this and how to make our buildings safe when these conditions exist. In tall structures, you would have this service stores, which may be a problem of weak story or open story. How to deal with them is one of the things that most of the structural engineer would struggle with. Then we have open ground story, we have weak stories, and then we have stories with infills, without infills, weak and open. So these are the configurations that are being covered in the code now. Weak and flexible story, and reduced column sizes. This is a very common practice that as we go higher up, the load is reducing, so we reduce the column size. It's a natural thing for an engineer to do, but we have to see that there's drastic changes are not happening in those structures. So this is a typical example of open ground story, because if you want to park a car, this is all parking area, and that is how the open ground story comes into the picture. This is a picture from a Jabalpur earthquake, where we noticed this for the first time. First time in India, a building which was an open ground story was subject to an earthquake, and we were able to look at it and understand what is the behavior. Theoretical knowledge before that was there in India, but we looked at this and we then came up with strategies of avoiding this, or doing an intervention which would reduce the effects of open ground story. So again, structural deficiencies, open ground story. The book that I talked about explains what are the effects, and pictorially they have tried to explain what will happen if this is the condition that you have. And then later in the book they also try to explain what are the methods that you should have. This is a weak story at the upper level. And irregular mass distribution. Again, heavy mass at different levels. This is possible in many of the buildings where you have a service floor which is having larger weight or mass which is there. So this will be the problem points in the building. Then we have irregular plan configuration. irregular mass distribution. So this is just a tip of the iceberg of what are the problems that can happen. Now, having knowledge of this, these are the problems that we have to deal with. Based on that, we go into the next step of identifying, and once we know what are the problems, we would be able to spot them and pinpoint them and say, okay, this is the problem, this is the solution that I want to have. So what are the options that we have available for retrofitting of a building now, or improving, upgrading, remodeling, all those 4 terms that we use. Basically, member retrofitting, where we do jacketing, wrapping, column jacketing, beam jacketing. Then we have structural retrofitting, where we add structural components, columns, beams, walls, into the existing structure. And there's material level retrofitting, where we add some material into the beam and strengthen it. Like epoxy grouting is one of the very common solution that is used everywhere, where you pump in some epoxy kind of compound and say that the strength of that has increased. So this is a common where we do jacketing of the column, remove the cover, put additional reinforcement and reconcrete it. This red is the original column, and the one outside is the new column that has been added, new jacket. The increase in size of the column is there. Then when there is a damaged portion, you can add reinforcement to the column and do a jacketing. So these are traditional standard methods that are being practiced across the country, where increase in size of the member, increase in strength of the member is possible. Here also, existing beam and a slab with existing the reinforcement of the column beam is not shown. When you add a jacket around it, you can do it like this. It's a very tedious and involved process. It takes a lot of time, and how to assess this, how to do an analysis of this, also a question. I mean, we don't understand this, how to do this, but such a large stock of buildings which are inadequate right now. These are the methods that are available for us. Then addition of new RC wall. We have to connect the walls with the members of the building, maybe the column foundation, create new foundation, connect it with the beam. And then this is the existing structure, and this is the new structure that is added to take care of the lateral load that is going to be subjected to. Then there is a method of adding masonry walls also, and this was practiced by many people. It was recommended also. Just go and add brick masonry walls into all the open ground, so just immediately after the Bhuj earthquake. And it is believed that this saved a few collapses of the building in the aftermath of the earthquake and then aftershocks of the earthquake. Original structure, and then you add infill walls, which basically adds a little bit of strength and stiffness to the structure. Then this is very rarely practiced, where you add an additional component or additional member outside the building. This is an existing building, you add a buttress wall outside the building. May not be very easily possible, but it's another method where you have space and where you have the luxury of encroaching away from the building. This could be another method where we can add lateral stiffness and strength to the building. Then this is commonly practiced across the world. India, few people are practicing this, where you add a cross brace in steel between the joints of the building, the panel of the building. This similar effect as the infill walls or the RC walls, but then in terms of having retrofitting, this is one of the repair techniques that is available. Then another practice that people have, they wrap this carbon fiber wrap to a column or a beam and increase the confinement, and that is able to increase the compression capacity of a member. So traditional methods, there may be many more which I have not covered. I mean, many engineers do different things, and they're able to come up with new methods which may not have been covered here. So we're looking at the pre-draft of 13935, third vertical column of the harmonization of the code, where we are looking at how to assess, repair and strengthen the buildings. This is the sample. This is not in the public domain right now. We are still discussing about this. Right now we have made a draft of the part 1, which is general provision for all structures. Like 13920 and like 1893, we will have different parts for different types of buildings, like for masonry buildings, RCC buildings, steel buildings, and all the other buildings that will come. Maybe bridges will also be covered in this. So looking at earthquake assessment of the structure, we have two types of assessment that we can think of: pre-earthquake, no earthquakes happened, and the post-earthquake. Post-earthquake has been done after the earthquake. Some of us would be able to visit earthquake damaged sites, but most of us will not get an opportunity to go into an earthquake damaged site. But pre-earthquake, what is to be done? Again, look at all the configurations of the building which are bad, which are good, and based on that try to assess whether the structure is good or not, and based on that decide what kind of intervention and what kind of strengthening is required for that type of structure. So this pre-draft is talking about 5 levels of assessment. The first one is rapid, quickly, within maybe 10 minutes, 20 minutes, half an hour, look at the structure from inside, outside, whatever is possible, and say whether there are major deficiencies in the structure, whether there's an open ground story, whether the columns are too small, whether it is sitting on a slope, whether it is on a sandy strata where it is liquefaction is likely. So these type of global features we identify in the structure and say that these are the problems in the structure and list it down. So this is a rapid quantitative assessment, similar to, you must have heard about rapid visual survey, where you cover about 10-15 buildings in a day. A group of 2-3 engineers, 2-3 technicians go and look at it and identify the buildings and say these are the problems with the building. The second is detailed qualitative assessment, where you put numbers to each one of them, each of the deficiencies which are a little more involved, but you need a little more experienced people. Put numbers to each one of them and then rank them. Then these are qualitative. Then the next 3 are quantitative, where you do preliminary quantitative assessment, where you see overall what is the structural safety margin, whether the base shear is okay or not, whether for the vertical loads that are coming on the building, whether the columns, walls, whatever structural system is available is adequate or not. Then we have basic quantitative assessment, where you check the building with respect to the existing codes or standards that you're going to use. And then there is detailed qualitative, where you do structural compliance with the standard with respect to the behavior of the structure. So you look at what behavior will happen in the structure because of these deficiencies, and then when you suggest a retrofit or a repair method, whether that repair method is adequate or not. So these are the 5 levels that we are proposing in the code right now, and based on, so that's how the 5 levels will come: rapid, detailed assessment, preliminary assessment. These are rapid 2 parts, 0 and 1. Preliminary assessment, quantitative here, then basic assessment, detailed assessment. So slightly higher level of effort for each of the levels. So this is qualitative, this is quantitative. So these are quick methods. This will require a little bit of analysis and design experience to do it. So we've tried to put this in a form of a flow chart. You do a 0 level rapid qualitative assessment. You check the critical aspects, prioritize the buildings. Suppose you have 200 buildings. In that, let us say, in this year I want to do 20 buildings. Based on the rank that you get here on the rapid, take up the first 20 buildings and go to the next step. Then do the detailed qualitative assessment of those buildings. And come back to this for the next 20 buildings the next year. Because the rank of that building is lower risk to that building. You take the first set first and start doing the work. So detailed qualitative assessment, then check all the earthquake features, assign the numbers to them, and say if the number is more than, let me go to the next slide. So when you assign the numbers to them, it's more than 90, it's a good structure. Then you come to this step here, preliminary quantitative assessment, do the overall check. If it is satisfied, nothing has to be done, structure is okay. If it is not, then you go to the codal provisions and come, and whether it's satisfied, come back and stop. So in this case, if it is between 60 and 90%, something is wrong with the building, do basic evaluation of the structure, the 3rd level evaluation. Check with the code. If it is satisfied, then you can stop. If you have structures not satisfied, then you go to the detailed evaluation. That's the 3rd, 4th level of testing, that evaluation that is happening. And that will happen for the buildings that receive a less than 60% score. That happens, and detailed qualitative assessment. For normal structure, there's one path given. For critical structure, there's another path given, because the main code, the IS 1893, is doing some kind of subdivisions of type of the structure, basically. So in this, you come here and check for code provision, not sufficient, develop a retrofit technique, check whether it's okay, sufficient. If not sufficient, then you have to go back and do this cycle. I mean, this is a design process, basically. For critical structure, you do code provisions and behavior also. You check the behavior of the structure also, check how it will behave before and after the retrofit measures. Come back and check all these features, configuration, strength, stiffness, deformability of the structure and the members, and then see whether it's sufficient or not. Sufficient, then you can stop. If it is not sufficient, go back into this. So a little bit of iteration is involved there. So quick summary. Rapid visual, identify major deficiencies which are life-threatening. In second, qualitative assessment, all the key features which are there in the structure, you identify a little more detail, where you look at site, where it is sitting, what is the problem with the ground on which it is sitting, the form of the structure, basically configuration, the structural load resisting system, material, and the construction practice or the construction type that has been used, whether it was good or bad. It could be, good construction done, you can improve the grade, the structures capability much higher. Then preliminary quantitative assessment is a basic check on just lateral loads, whether VB in X direction, VB in Y direction, adequate or not. Based on the understanding of structure, quickly we can calculate what is the base shear, and then go with the capacities which we are able to identify from the standards, and check the design and see whether that satisfies. The third one is compliance with the standards. Do a detailed analysis of the structure, check all the equilibrium equation laws, constitutive laws, and compatibility. Do the design based on that, like when we spoke in the beginning of this presentation, where we make all our assumptions, where we collect all the documents and take leaps of faith and say that this is my structure, assume the reinforcement, all that. After doing all that, we come up with the understanding that the structure can be passed through this kind of an assessment. And then the fourth level, or the fifth level actually, 0 to 4 is the fifth level. We see whether the compliance is there with the code, including the behavior of the structure. So this basically look at the performance and how it will behave, and based on that actually do the assessment of the structure and qualify the structure. So this in a nutshell is what the 13935 is trying to achieve, and that is how the code is being drafted. So outcomes is the answers to what is the structure safe and what and where the deficiencies are. All the critical problems that can happen in the structure, compare them with each other and say that this is a critical structure or not. Even if the structure may not collapse, what level of damage would it sustain given a design level earthquake to occur? And main assessment whether the method is going to give you what you are trying to achieve. So I'll quickly go through this, what rapid visual assessment or rapid qualitative assessment is. You identify the major deficiencies in the building, make on the current housing practices, document all the. So I will not go through this because there are many slides in this. In a nutshell, I'll say you identify good characters in the building. Make a list of that and compare it with the building that you're looking at it. Suppose the building has an open ground story. You say, okay, this is an open ground story. Open ground story is not good. It has a weak story. It's not good. It has a column which is undersized, not good. Mark that as a negative point on that building and go ahead with the assessment. Then these are the features that we look at. Materials, who has constructed it, what are the methods that were used, whether it was good construction, bad construction. And this has to be done for different types of building. One is for the houses, whether it could be masonry houses, could be RC buildings, could be bridges, or it could be steel structures, any type of structure that we have. So we are going to have the same strategy which we are going to have for 1893 and 13920, where we will have the main code and then attachments to the code or subsections to that code of dealing with each of these typologies. Frame structure, truss structure, mixed structure, good and bad comparison, where you say that, okay, this is good, this is not good. And in that, again, you look at structural and non-structural elements, assign ranks for each one of them. If this is the problem, if you have, let's say, a TV or a heavy mass sitting on top, which is likely to slide down and fall and cause life-threatening conditions, then you give a higher level of negative marking to that. So S factors and N factors. So those will be life-threatening and economic losses factor. So in this, we do this. All the good features are listed on one side. compare it with your building that you're looking at, and give negative marks to the buildings if these good features are not present. So that is how we list the building, create a rank system, and take the top ones which are the worst buildings and go ahead for the next this. So this one code has already come out by CV 39, which tells you, this looks at all the critical aspects and do a rapid visual survey. There's a form which is given in the code, which is, it can be updated quickly or can be updated based on the inputs that we get from the practicing engineers. But that basically code tells you how to do a post-earthquake safety assessment of building. After the earthquake, how do we look at the buildings? And it has covered 2 or 3 types of buildings which are commonly available in this country. Then you have a detailed qualitative assessment where we do, this is again qualitative, where we look at all the features in much more detail. There is a structural features and non-structural feature, again life-threatening and economic. So these two go together. With life-threatening, if it is more, then you assign a larger negative marking. If it has economic loss, larger negative mark basically. So that's how the ranking system is created. All the good and bad are compared with each other. Good is listed, compare it with the structure that you have. And we take guidance from existing document, past experience, past people who have worked in assessing buildings. And then you assign this factor for structural, non-structural. Once these are given, then you compare it with the best building and say this is the structural deficiencies that we have. So different types of buildings can be covered, which are houses, stone masonry houses, houses with stone or brick. Then there are some features in the building which could be bad. You list them down and give a negative mark to that. And then in there's a method called Delphi method, which basically tells you how to do this, and they have listed a lot of features which are good and bad features. So look at those features and identify the buildings which are marked. So here if you look at one of the examples which has a sighting issue, which the entire house is on the ground floor, then this is the ideal condition. Then house is sloped ground with access to 2/3 of level, you assign a negative 5% mark to it. So good building compared with the existing building, and then you add all this mark and see what is the level of the building, and do this both for economic and life-threatening features. This is called the research Delphi method, which is more involved. The second method is the Delphi method. You talk to people who look at the building and assign a ranking to the building. And there's a mini Delphi method, which basically is used in that code that I showed you, where you look at the building, make estimates, talk to people, and then say that this is the condition of the building and this is the rank to assign to the building. Then we have preliminary quantitative assessment, where we say check for basic load configuration, X direction, Y direction, whether they are okay or not, check the design. Some examples are given here. One of the bridge which can be quickly checked for earthquake load that will come on that, and whether this bridge is okay or not. So some features that need to be connected, I will skim through this. Basically, if there's a bridge, you check in both the direction forces that are coming and check whether the seating, bearing, bolting connections for the bridge is okay or not. This is a picture from Uttarkashi earthquake, which the bridge had collapsed and abutment collapse. Again, another picture. Here there's another picture which shows the shearing of the bearing. The bearing which was connected to the abutment and the bridge actually sheared off. A closer picture. So again, connections play a critical role in making the structures safe. So this example, look at bearings, look at bolting, look at seating, look at overall lateral capacities, and look at lateral restraints if there are any. This is an example for the bridge that is created. Then we have basic evaluation. Again, 3 features that we look at in this is the stiffness, minimum stiffness, configuration of this, minimum stiffness, minimum strength. This is the code level compliance that we are looking at. But very basic, we do linear analysis, check it with the design codes, and check it with the load and design strengths of the provision of the codal provision, and see whether the structure is okay or not. And based on that, you go yes or no, and then take the next step. Detailed qualitative assessment basically involves doing a detailed analysis and combined with the behavior of the structure. And when the behavior is good, all these 7 features have to come in the structure, which is configuration, stiffness, strength, ductility along with deformability, good collapse mechanism, and energy absorption. So these 7 features, I'm sure you are now familiar with this. Even RUPEN has showed this, and I have showed this at least 3 times in this presentation. So key aspects is this type of 4th level of analysis. 4th level of assessment will require some kind of nonlinear analysis, understanding of what are the behavior of nonlinear analysis. So if you look at detailed qualitative assessment, we have configuration, stiffness. Behavior wise, I'm showing you how it will show in a nonlinear analysis. Strength, ductility, deformation, and mechanism and energy absorption. So this is for an earthquake. If you're doing a back and forth loading, this is how the behavior, you would be able to visualize the behavior like this. In closing, we have different levels of assessments, 0, 1, 2, 3, 4, and very large stock of buildings will need the first, let's say 30 crore buildings in the country. Then second level will be required only 3 crores. So third level will be required for 30 lakhs, and 4th level is required for 3 lakhs. So that is the kind of effort. As you go down in the level of evaluation, number will come down obviously, but the effort increases. So that is the goal of this code. So right now we are in the mode of prescriptive. Our codes are very prescriptive. You do this, you will get this. Or we're not saying we will get this, but these are the good things to be done, and then you will achieve a good structure is the message. We have to move towards qualitative assessment, qualitative to quantitative. And the 4 parts of safety assessment are surveying. Basically, we have to understand, collect documents, understand what are the deficiencies, and be able to compare them with ideal structures. Then screening, again, screening the process of doing a large stock of buildings, and step by step. If you have 5,000 buildings, you do 1,000 in first year and then 2,000 in second year. Then shortlisting of structures using detailed analysis, and then safety evaluation, which will need some kind of nonlinear analysis. So again, looking at this chart, again, you examine the documents as a beginning, inspect the structure. This is the same chart, is present in different way. If you come to a point where the extent of damage is so much, then you take a decision that you need to deconstruct and demolish the building. So that is the idea of revising this chart and showing it slightly different way. It involves a lot of estimation also. The cost is an important factor where you say whether the structure should be retrofitted or not, whether it is economical to retrofit the structure or not. But all structures cannot be demolished. So it's a balance that we have to play as structural engineers and maybe planners and designers, whether the structure can be demolished or it needs to repair. So identify demolished deficiencies, decide the intervention, do again this economical evaluation whether retrofit is possible, retrofit, not demolish. So both paths we are trying to say or provide in the course, so that the structural engineer is empowered with this, taking a decision either way, whether to demolish or not. Recommend, undertake the retrofit, and that's where you stop. And that's all I have. Thank you very much, and I'm grateful. I would like to apologize. Professor Murthy was supposed to be here, and Professor Murthy has also asked me to specifically apologize to all of you. I know you were expecting him, but for unfortunate reasons he's not here. But I hope, I'm sure it was not Professor Murthy, but I hope this was a little bit of information has been transferred for us. Thank you.